Okay, let's talk about this rewind problem. So what's the first thing we do always? Write down the givens. So my givens here are Q is the midpoint. I'm going to abbreviate it, MP. The second one is angle L is equal to angle P. And the third says LM is congruent to NP. All right, so those are all 1, 2, 3, and that's all given. All right, if you know that Q is the midpoint, what else can you say? If you know Q is a midpoint, what else can you say? What does it mean for something to be a midpoint?
It's that they're congruent.
What's congruent?
The LQM and PQM.
Those are our angles. We're not talking about angles yet.
Then it cuts it exactly in half.
Cuts it exactly in half, right? So if Q is the midpoint of MP, then what do you know about PQ and QM? All right, so PQ is congruent to QM. What else do you know?
I said it, right?
Not the angles. It's also the midpoint of LN, so what else do you know? LQ is congruent to QN. LQ is congruent to QN. And that's based on what? Definition of midpoint. All right, so now we know that. We already know that this side is congruent to this side because that's a given. And then we know that angle L and angle P are congruent. So Tiara, what else can you say? What else can you say?
That LQM and PQM are congruent.
This angle is congruent to this angle. Why? Because they're vertical angles. Good. So I know that LQM is congruent to PQN because of vertical angles. I'm just going to put vert angles. All right. And once you have two of them, what do you know about N and M? They have to be congruent because of the third angle theorem. All right. A theorem has, a postulate is 100% true. There's never any doubt of it. A theorem is like probably true, but no one's proven. You'd have to come up with every single counterexample and prove that those are true to consider it like a postulate. So we call it a theorem because maybe in some alternate universe this might not be true, but for the most part it is. All right? So that's based on the third angle theorem. So we say angle M is congruent to N based on, that's 7.
Wait,
I missed a step. 4, 5, 6. You should be confused because I wrote that wrong. All right, so that's the third angle theorem. And now I'm done. Why? I have all the sides and all the angles, so now we can say that triangle LMQ is congruent to triangle NPQ. And that's based on
What would be the third angle?
definition of congruent triangles. All right, definition of congruent triangles. That was long. That's a lot to know, right? Wouldn't it be better if we didn't have to prove all of that? Yes. So what we're going to start talking about now is we're going to start talking about ways to prove that triangles are congruent without having to prove all 6 sides, and all 3 sides and all 3 angles are congruent, all right? Because there's shortcut ways of proving that all the triangle is congruent without having to prove all 3 sides, all 3 angles, because that's a lot of work, all right? That's a long proof, and it shouldn't have to be that long. So we're going to talk today about two different properties that we can use to prove that triangles are congruent. So do we need all 3 sides and all 3 angles to prove that triangles are congruent? No, you don't. You don't need all that. That's a lot of information, and that's going to work every time, but you don't need all that. You can prove that a triangle is congruent using a couple different shortcut ways, and today we're going to talk about SSS and SAS. All right, so SSS postulate is called side-side-side congruence, which says if you know that the 3 sides are congruent to each other, then that's enough information. All right, so if you prove that the 3 sides of a triangle are congruent, then the 2 triangles are congruent to each other. And that's called SSS, which stands for side, side, side. Good. because you could technically have like 1 and 2, and this one could be 3, or you could have like, it doesn't necessarily have to be like the same. The third side doesn't have to be the same just because the other two are. Like you could have a triangle with 1 and 2 that is like an isosceles triangle like this. So just because this was 1 and 2 doesn't mean the third side would have to be 3. Does that make sense? Like 2 sides is not enough. You need that third side. Because technically like this one is 1 and this one is 2, but that one's 3. This one is 1 and this one's 2, but that one's 2 also. So it's 2 sides is not enough. You need the third one. So side, side, side means that all 3 sides are congruent and all 3 sides are congruent. So then you can say that the 2 triangles are congruent. So going back to that rewind problem, that means we would have been done with this proof right here. We could have stopped right after 4 and then said that the triangles were congruent because we already had the 3 sides were congruent. Does that make sense? Yes? Okay, instead of having to go all the way through. So it would only been 5 steps instead of 7.
How do you find that Pn is congruent to the other one?
To LM, it was a given. Yeah. We wouldn't have been able to otherwise. But it was, since that was a given, we could figure that out. Okay. All right, so side, side, side means that we can use that because look at these 2 triangles right here. We want to prove that PQR, which is this top triangle, is congruent to PSR. Right now, what sides do I know are congruent? I know that QR and SR are congruent. Okay, and I also know QP and SP are congruent. That's only 2 of them.
But I think, because like, the angle by P and, I don't know. It's like the same triangle. It's like
You guys are saying the same thing. PR is part of the top triangle and the bottom triangle. So you can say that PR is congruent to PR. What property is it where one thing is identical to the other? No. Marina? Marina? Yeah, it's the reflexive property. So you can say that they are congruent because of the reflexive property. Because remember, reflexive kind of sounds like reflect. It's like a mirror. It's the exact same thing. So PR is congruent to PR. That means that that triangle is congruent to the other one because all 3 sides are congruent. All right, so PR and PR are congruent. So do you have to say that? Yes, because it's not marked on there. So you have to say PR and PR are congruent because of the reflexive property. Now you can say PQR is congruent to PSR based on side, side, side. All right? And so we just abbreviate it using SSS for side, side, side. Yep. All right, so that's what the 2-column proof would look like for that problem. These 2 are given because they told you that those were congruent. That's congruent based on reflexive property. And again, you're going to use the reflexive property when this right here is what? In the middle, when it's a shared line. So when one line acts in both triangles. She's not even here. You didn't ask her if you could have that. All right. Side, angle, side, SAS, is enough to prove that a triangle is congruent if you have 2 sides and an angle, as long as the angle is where? Is included. What does that mean, included? In between what? The 2 sides that you have. Okay, so this 2 sides, this is congruent to the green side is congruent to the green side. The blue side is congruent to the blue side. The angle that's included is the angle that is made when you connect those 2 lines. Okay?
Isn't that the same thing as corresponding?
It's like in the same spot? Yeah, corresponds to it. Yeah. So for instance, if you had this triangle, QRS, and this triangle, LMN, and I gave you QR is congruent to LM, RS is congruent to LN, and this angle is congruent to this angle, would that be enough?
No.
No. Why not?
Because it should be in between or L's at.
It would need to be L in this one. Because is this angle included? No. If I draw this, that's not the angle in between. The way that I remember that is it's called SAS. So it should be the side, the angle in between, and then the side. So when I highlight it with my hand, it should go like side, angle right here, side right there. All right, so side, angle, side means it's the side, the angle in between, and the other side. All right, those are the two theorems we're going to talk about today.
Kind of like perpendicular?
What do you mean? Where they meet, yes, but they don't necessarily have to make a right angle. So they're intersecting, but they don't necessarily make a right angle. So if you want to think about it like that, that works, just not necessarily right angle. Intersecting, not perpendicular. Okay. So could you use that to prove A, B, C, and D, E, F are congruent? What angle would you need in this one to use side, angle, side? E. Why? Because E would be the included angle. Okay, go do these four. Hang on. State if the two triangles are congruent. So tell if they are congruent based on side, 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 or side, angle, side. So it's either going to be yes, and then give a theorem, or no, not congruent. Good morning, Miguel. All right. Okay, so show that the triangles are congruent for the given value of the variable. So take a look at these triangles. We have triangle UVW is congruent to YXW if x equals 3. So what do you have to do first here? Jennifer?
First of all, they can't be congruent because the triangle there is x equals y.
What?
The triangle in the picture is x, y, z.
Oh, that's true. All right. Well, that's a typo. So this would be UVW and X, Y, Z. All right. Good looking out, Jennifer. All right. If, in fact, it had said X, Y, Z, what would we do to confirm that these are congruent?
Plug it in.
Plug it in. So if I plug it in here, if X equals 3, what is XZ? 3. All right. What is ZY? 2. And what is 3X minus 5? 4. Okay, so are these congruent? Yes, based on what theorem? SSS. So postulate SSS, these are congruent. So we would say like congruent by SSS. Okay, so how are we going to use these, bless you, how are we going to use these in a 2-column proof? Put the givens first. Thanks, Charlie. So our first given is L is parallel to M. And our second given is EG is congruent to HF.
I just said it wrong. It's line HG or segment HG is congruent to EG.
It's not HG.
EG is congruent to segment HG.
Thanks, Tiara Johnson, student at Cristo Rey Jesuit. All right.
They're gonna know our school. Oh yeah, you just pop that out.
I don't think people are going to be going onto this account. I'm not that worried about it.
Oh my gosh, wow.
Okay. All right. So we have that L is parallel to M and EG is congruent to HF. So we want to prove that the triangles are congruent. We want to prove that EGF is congruent to HFG. So they already wrote on here in this picture, we've got the little red dashes, which mean that those two sides are congruent, and we know that those two lines are parallel. Can anybody tell me anything else? Bianca? Good. GF is congruent to GF. Those two sides are congruent based on what? Good. Based on the reflexive property.
I still
because you have to know either all three sides or two sides in an angle are congruent, and GF is part of both triangles. So this is like the GF from the triangle on the left, and the second one is like the GF of the triangle on the right. Does that make more sense? So now I know that this triangle and this triangle are congruent. So sometimes it helps if you look at it like this is EGF, and this is triangle GFH. You need this side to be congruent because that's two sides of the triangle. So if they were separate triangles, you would have to figure out those two sides. Since they share a side, you just have to say that they're congruent based on the reflexive property. All right? Okay, number 4. What else can I say? Not going to call on you right now. Give me 1 second. Anyone else?
They're parallel lines, guys.
Think about your other givens. So think about the other given. It doesn't tell you this for no reason. So it doesn't tell you that L and M are parallel for no reason. Okay.
Alternate interior.
What are alternate interior?
Angle G and angle F.
What do you mean by angle G? I only say that because there's like two angles there. So which angle are you talking about? So like EGF? This one right here? Yes, that one right there? Good, yes, that's what you meant. Okay, so EGF, and then which one here? GFH are congruent. Okay, so Gabe says that EGF is congruent to GFH based on alternate interior angles. Because if these two lines are parallel, this is a transversal, so those angles must be congruent. So why did I say he couldn't just call it angle G?
Because there's no G.
There's like 3 G's actually. There's 3 angles that have a vertex at G. Okay, so now you have what? One side, another side, and an angle. So can you prove that they're congruent?
Yes.
Good. So we would say that triangle EGF is congruent to triangle HFG, and that would be based on what? Side, angle, side. SAS. SAS.
You're going to have to explain number 1.
I got it. No more deep in it.
Okay, so again, just to reiterate, would it have worked if it was a different angle? Could we have used SAS if it was a different angle? What's special about this angle right here compared to these two sides?
Wait, that is alternate interior.
Yeah, also because it's the included angle. And again, what does included angle mean?
Same spot.
Same spot. If I give you this angle, or this triangle, CEL, and I say CL and CE, which would be the included angle, CE or L?
C. S. S. C.
Why C, Charlize?
Because it's between the middle.
It's between these two lines. So this is the angle that's included because it's between those two lines. All right, so going back to that proof, you would need this angle, this EGF and GFH angle, because that's the one that's included. Otherwise, we would have had to prove other stuff. Okay, questions on that? Okay. All right, so you guys can go ahead and do your exit ticket on the template. If you didn't get one, they're sitting on the desk.